Hi, I'm Nick Pettit, the lead Unity developer at Buck. By the end of this video, you'll know how to install and use Save Async, our free and open source Unity package for asynchronously saving and loading data in the background. First, you'll need Unity 2023 or higher because the package uses Unity's new awaitable class, which is not available in earlier versions. With the Unity project open, copy the Git URL from the Save Async repo, and inside of Unity, go to Window, Package Manager, then choose the plus button in the upper left, and install package from Git URL, and then paste the URL and click Install. Next, I also strongly recommend you install the Unity converters for Newtonsoft.json package for better serialization of Unity types. Let's go back to the GitHub repo and copy the URL for converters for Newtonsoft. And let's go back to Unity, hit the plus button, install package from Git URL, paste it, and click Install. Now, with both packages installed, let's check out the sample project that's included with Save Async. I'll select the package, choose Samples, and then click Import. This will add a samples folder to your project where you'll find the example scripts and a sample scene. Let's go to that folder and open the sample scene. And then let's hit play. Now I'm going to select the component called GameDataExample, which is one of the components that will have data saved and loaded. If I click Save Game Data multiple times, it will show me how long each disk write takes. The first one is always the longest, but after that, it tends to be faster. And now, if I change the data in the GameDataExample component, and then I hit the Load Game Data button, it will restore the data that was originally saved. The file handler included with the project uses Unity's persistent data path, which will save to the correct locations across many different platforms automatically, such as PC, Mac, and mobile. In Unity's menu bar, Save Async will add a menu under Tools, Save Async, where you can open the persistent data path that I just mentioned. And this will vary depending on what platform you're on, but on my Windows computer, it looks like this. Here you can see some of the files that are being saved by this example project. And when I open the game data file, we can see that the contents are stored in an unencrypted JSON format that we can read. It includes some of the serialized fields that we saw in the inspector, along with some other test data that's not shown in the inspector, meant to represent things like player inventory that might change at runtime. There's also buttons here to erase the contents of the files while still leaving them on disk, or delete the files entirely, but I won't click those for now. Over in the inspector, there's a game object called Save Manager, and it has the Save Manager component attached to it. This is a singleton class, meaning that only one should exist at runtime. The first step of setting up Save Async is to add the Save Manager component to a game object in your scene. It's from this component that you can optionally choose to enable encryption for your save files and pick a password. If you want to learn more about that, check out the README on GitHub, but we'll ignore this for now. With the Save Manager in your scene, let's take a look at how to set up data we want saved by opening the script for the GameDataExample that we looked at earlier. Any class that you want to save needs to include the Buck Save Async namespace and implement the interface iSaveable. The interface has a public property for a globally unique identifier, or GUID, a string property for the file name representing the file name this object should be stored in, and two methods, one called capture state and the other called restore state. Let's go back to the game data example class and see how they're implemented. Every object that's savable needs a unique identifier so that when a save file is loaded later on, the data in the save file can be matched to the corresponding object in your scenes. To do that, we need a serializable GUID to be saved in the scene. This is admittedly a bit tricky, but the Save Manager can help us here, and I'll go step by step. So first, since Unity can't serialize GUID types natively, we need something that Unity can serialize. So you should create a serialized byte array to store the GUID. And ideally, you should hide this in the inspector because it's not something that you should ever need to modify. Then, to implement the iSavable interface, there should be a publicly accessible GUID property that creates a new GUID using the byte array. Finally, you should use the monobehavior onValidate method to call the SaveManager.getSerializableGUID method and pass in your byte array with the keyword ref. This way, whenever you switch back to Unity, your class will automatically have a stable and serializable GUID, and if it doesn't, a new one will be created, which is what happens the first time you load this up. Next, we need a string property called filename. This is to store the path or the name of the file where this data should be saved. You could just type your own string here, but I recommend you create a separate static class that stores your file names as constants. That way you can just type a variable name and avoid typos that could accidentally create multiple files. Now, down here, I have some hypothetical game data like the player's name, health, position, and a dictionary representing an inventory of items a player might have. And above that, I have created a custom struct called myCustomData. And while you can name this whatever you want, you'll need some kind of object like this that you want to save. And you should then add the serializable attribute, which is in the system namespace, to allow it to be saved by the Save Manager. Next, iSavable needs to implement the methods captureState and restoreState. CaptureState will be called anytime the game is saved, and it should return an object representing your save data. In this case, I'm creating a new custom data struct and setting all of its values to the current values in the class. RestoreState will be called anytime the game is loaded. It takes an object in the method signature, and then in the body of the method, you should cast the object to your custom data type. Then you can restore the state from the object variables. Finally, in the awake method or somewhere in the early initialization of your class, you should call SaveManager.registerSavable and pass it this so that the Save Manager knows about your object. The sample project also includes another example implementation where cached data is passed to captureState. So let's take a look. We can type in another string here, type in an integer and a float. And if we hit save game data and then load game data, none of our data will be loaded. And that's because we are caching the data at a different point. So I'll type some more data here, say some string, we'll type an integer and we'll type a float value. And then in the context menu, we will choose cache data state to simulate caching the data at a different time than when capture state gets called by SaveManager.save. Now that we've cached the data, we can hit save game data and we'll change this to something else. And then if we hit load game data, it will restore the data that we had at the time that we said cache data state. So let's open up the script and take a look at what's actually happening here. So down here, we have the method cache data state. So in other words, you can hold on to your data at various points in your game, and then only when capture state is called do you actually commit it to disk. This is advantageous if you don't want capture state being called at an unexpected time when maybe your data is in an odd in-between state. So back in Unity, again, you can simulate that by hitting play, going to the context menu and choosing cache data state on this component. So now that we know how to prepare classes to be saved and loaded using the iSavable interface, we need to tell the save manager to write to disk and read to disk. This part is more straightforward, and to see an example, let's open the script for the game manager example component. This script contains methods that are being called by the buttons in the scene. If benchmarking is enabled, which it is right now, it will take a code path that gives you the text output in the scene that you saw, showing how long each operation takes. But more normally, you could simply call methods like savemanager.save or load, erase, and delete. All you need to do is pass in the string for a path or file name, or an array of strings for paths and file names on which you want to perform file operations. So using this approach, you could, for example, save a settings file every time the player closes a settings menu, and then save a more normal game file when the player reaches a checkpoint. So that's Save Async in a nutshell. We needed it for our own game projects, and we're happy to be able to share it. If you're interested in contributing or need some help, feel free to open an issue or a pull request on our GitHub page. Thanks for watching.